Good day, class. Welcome for another lecture for our subject Hydraulics Engineering. Today we will talk about major losses. This is divided into two parts. So part 1, head losses in pipelines, and in part 2 we will discuss the major examples that requires iteration, the difficult problems. Okay? So let's begin. Essentially, losses of head in your pipe or in your water flow came from friction. Okay, so and as we said from the previous lectures and early on in your mechanics, in your statics, in your kinematics, we already have an idea that friction causes energy dissipation. Okay, so energy losses through friction in the length of pipelines is commonly termed the major loss, H sub F or HF. Let's term it HF. So the pipelines or your pipes have rough surfaces that causes the dissipation, the friction energy. So this is the loss of head due to the pipe friction and the viscous dissipation. Take note of the term dissipation in your flowing water. So some studies and some researchers have found out that resistance to flow in the pipe is independent of the pressure, proportional to the pipe length, inversely proportional to some water power of the diameter d, and proportional to some mean velocity and related to the roughness of the pipe. So class, all of the following, these terms are the pressure, the length, the diameter, the velocity, the roughness are all dependent of your energy equation, right? So from your Bernoulli, these are your variables. So it is just valid to conclude that friction is connected with these variables or these functions. So as I said earlier, that energy head and head loss in pipe flow are concerned with energy. So it can be visualized here in this diagram that's showing the energy grade line and the hydraulic grade line. Okay? So major losses formulas that we will also discuss in this lecture are the following. So several formulas have been developed in the past and is faithfully used up until now. The resistance to flow in a pipe is a function of, as we said earlier in the first slide, the pipe length, diameter, velocity, the properties of the fluid. So your fluid may not be water only. So your fluid may be oil, maybe gas, and so on and so forth. The roughness of the pipe. So the very basic equation of the Darcy-Weisbach, which is the most commonly used equation for head losses, is the following. Okay? So it's a function of your friction, your length, your diameter, your velocity, and your gravity of acceleration or constant of acceleration due to gravity. And the friction factor is concerned or a function of your Reynolds number and relative roughness. For laminar flow, or where the Reynolds number is less than or equivalent to 2000, we can have this function or this equation, F is equal to 64 over the Reynolds number. Take note again, class, that NR can be R. Okay? So for turbulent flow, greater than 4,000, we can use this. For smooth pipes. Okay? So for transitional flow, 2,000, in between 2,000 and 4,000. So some other functions that we can use or equations. Class, don't need to memorize these formulas. Okay? So we are not engineers to memorize formulas. We are engineers to have manuals, to know how to use those manuals, and to make life more efficient. Okay? So another formula for Pantel-Colebrook equation, where it is known as the Karman equation from the, what is this? Hydraulics manual. Okay? So the friction factor is dependent, as we said earlier, for the following. So if you have a delta, an increased delta, we assume that it is not hitting your pipe wall. So the flow is smooth. Okay, so as you decrease the flow, imagine this. Uh, your pipe wall having this rough surface and your fluid is hitting it very hard. Essentially, there will be chaos in your flow, right? There will be disorder. That's why your turbulent flow can be seen in your rivers, in your flash flood, in your raging waters, okay? So your turbulent flow, where the Reynolds number is more than 4,000. So smooth sailing, rough flow, okay? So the Moody diagram essentially is a very important chart prepared by Lewis Moody. That's why it is termed as Moody diagram. So the laminar flow. So from the earlier equations, that is simply a function of the Reynolds number. The critical zone, the transition zone, and a zone for fully developed turbulence with this diagram. Okay? So the Reynolds number is in the horizontal axis, the friction factor, and the relative roughness. So don't worry, class. We will have many examples uh, solving problems in application of the Moody diagram. Okay? In order for us to determine head losses. So here's a sample diagram also. So the laminar flow here. So dependent only by the Reynolds number. 0 to 4,000. Okay? So this is noted as critical from your 2,000 to 4,000 because it is considered as your transitional flow. So but in here, it behaves linearly. 64 over RE. Okay? Next. So some other formula is the Colebrook formula, valid for turbulent flow, with the function of this equation. So in fact, the Moody diagram or the Moody chart is a graphical representation of the Colebrook formula. So I will give you an example before I'll show you this. No, I will show this the solution. I want you to find a theoretical formulation for frictional factor for laminar flow. Okay? So we are also concerned with the absolute roughness. So again, the pipe properties is very important. So your pipes may be made up of plastic, may be made up of iron, may be made up of steel, may be made up of copper. So it is dependent. So your relative roughness or absolute roughness is dependent from your pipe materials. So these are the common values. Take note of this. Okay? So for your material roughness, this one. Now let's look on these problems. So three types of problems that we will discover how to answer. So for type 1, given the size and the kind of pipe and the flow rate. For type 2, given the kind and size of pipe and the head loss, where to identify the flow rate. And finally, given the kind of pipe, the head loss, and the flow rate, where to identify the size of pipe. So take note, class, when you talk about the head loss, this is essentially your energy loss. For your flow rate, essentially you need to have the velocity. Area multiplied by velocity is your flow rate. So finally, for your size of pipe, this is essentially your diameter of the pipe. Okay? So for type 1, given the kind and size of pipe and flow rate, we are to identify the head loss. So this is very basic. We're just to use the equations and of course, the Moody diagram. So example number 1. So from the example, with the water flow in an asphalted cast iron pipe with a roughness of 0.12 millimeters has a diameter of 20 centimeter at 20 degrees Celsius discharge. At 20 degrees Celsius. The discharge is 0.05 cubic meters per second, and we are to identify the loss due to friction per 1,000 meters or 1 kilometers. Now we are to identify here the losses. Essentially, that is the head loss. Okay? So that will be a type 1 problem, given the kind and the size of pipe and the flow rate. So this is your flow rate, 0.05, and your size of pipe, diameter 20 centimeter, and the kind of pipe is an iron pipe with a roughness of 0.12. First step is to identify the velocity. So as we said earlier, that area multiplied by velocity is your discharge. So this is very basic. The discharge 0.05 divided by the way, class, the most common cross-section of your pipes is the circular. That's why we will always use circular pipes. So pi over 4 for the area is 1. Okay, the diameter squared. So solving further, we will get the velocity as 1.59 meter per second. Now for at temperature degrees Celsius, the kinematic viscosity is 1.01 times 10 to the negative 6. So usually class, this is given. Okay. So, or if it is not given, it can be identified from your tables. So roughness 0.12 millimeter given. So relative roughness of E over D will give us 0.006. 0.0006. Sorry about that. And solving for the Reynolds number, that is simply the velocity multiplied by the discharge divided by your kinematic viscosity. Another equation can be used here is the rho Vd over mu, or the density multiplied by the velocity multiplied by the diameter of the pipe divided by the dynamic viscosity. Okay? So, but in this case, we will use the kinematic viscosity. So, essentially, we will get, for the Reynolds number, 3.15 times 10 to the 5 and Moody diagram of 0.018. Where did we get this? So, looking at the Moody diagram here, we have here at 0.0006, and then at a Reynolds number of 3.15 will give us this line, okay? Will give us this line. So, looking further on the left side will give us the friction factor. What is this number? It is basically in between 0.020 and 0.015. And that is your 0.018. Sorry about that. Okay? So solving further for your head loss, the friction factor from the Moody diagram 0.018 multiplied by the length per 1,000 meters per 1,000 meters or 1 kilometer divided by 0.20 multiplied by the velocity squared divided by 2 multiplied by the acceleration due to gravity. So your head loss is simply 11.55 meters. Very basic. Okay? So, if you will have questions, you may comment down in this video. Message me personally in my email address or message me in Facebook. Another example, the water flow in commercial steel pipe, again given the kind of pipe, has a diameter of 0.5 meters at 20 degrees Celsius. Given also the discharge, we are to determine the head loss. Again, this is a type 1 problem. So, solving for the velocity, it is just simply the discharge divided by the area of the pipe. So 0.5 squared, that came from the diameter, multiplied by pi over 4 will give us the velocity of 2.037. So actually, class, this is the formula for the kinematic viscosity. So 497 times 10 to the negative 6 divided by the given temperature plus 42.5 raised to 1.5. So the kinematic viscosity is simply 1.006 times 10 to the negative 6. So that is your solving for the Reynolds number. What is this? Velocity, the 2.037, this one, multiplied by the diameter over the kinematic viscosity, 1.006 times 10 to the negative 6, gives us 1 times 10 to the negative 10 times 10 to the 16. And solving for the relative roughness, 0.045 divided by the diameter. Oh, take note of this, class, ha? You have a diameter of 0.5 meters. So it is equivalent to 0.15 or 0.5 times 10 to the 3. Why? Because we are concerned with millimeter in order for the units to cancel out. So take note that the relative roughness is absolute. No units. Okay? So let's look for the Moody diagram again. At 9 times 10 to the negative 5, where's that? So about here. About here. About here, class. Okay, then, uh, so I forgot to copy paste the, so let us look again for the friction factor here. I'll copy the diagram for us to look very easily. Okay, so at 9 times 10 to the negative 5 at the roughness, so this will be here. So about here in this area. Two, three, four, five. Okay. Okay, so I have arranged this, class. Sorry about that commercial break. So 1 times 10 to the 6, and your Reynolds, that is your Reynolds number, okay? So for your relative roughness, 9 times 10 to the negative 5. So, looking further for our Moody diagram, so 9 times 10 to the negative 5 is simply here. And your Reynolds number is about 1 times 10 to the 6, okay? So, at this, sorry about the straight line, but it's supposed to be curvature, no? The curvature, right? The curvature line. So, something like this. So, curving. Okay? So, from that diagram, with intersection of 1 times 10 to the 6, will give us a friction factor of in between 0.01 and 0.15. Right? So, that will give us your 0.013. So, solving further, your 0.013 multiplied by the pipe length, multiplied by the velocity squared, divided by the diameter of the pipe, multiplied by 2 times the acceleration due to gravity. So, basic answer. Another equation, we can simply use the Colebrook. So, again, we have series of equation to use. So, it is your choice. But if I want you to solve again, if I want you to solve using Moody, you must use Moody diagram. Okay, so in this case, you just need to substitute. It's very easy, right? So, using the Colebrook equation, inputting everything, the relative roughness, that's the only one na known, and the Reynolds number. So, identifying will give you simply the friction factor to be 0.01334. So, almost equal from our 0.013. Okay? So, solving further, your head loss is 5 meters per kilometer. Almost equal here. Okay? Equal. 5.5 kilometers. So, you may also use the Pantel-Colebrook equation. So, again, just inputting the constant or the values will give us a friction factor of 0.012, which is also close to 0.013. So, again, you substitute this from your Darcy-Weisbach equation, will give you the same answer. Now, how about for problems of type 2? Given the kind and size of pipe and where to determine given the head loss, where to identify the flow rate. So essentially, you need to have the velocity. Okay? You need to have the velocity. And multiply the velocity by the area for you to get the discharge or the flow rate. So, let's look. So, these are just guidelines, right? So, let's look straightforward. So, you just need to identify from the Reynolds number. So, actually, this will be our last equation for the part 1. So, given this diagram or pipe with uh, pipe at or pressure at point 1 is 150 kilopascal and pressure at point 2 is 120 kilopascal with a length of 30 meters and the height of 3 meters. Okay? So the fluid is at kinematic viscosity of 10 to the negative 6 with a density of 800 kilograms per cubic meters and flows through an 8 centimeter. Take note because this is your diameter. Okay? So, in order for us to identify we are tasked to find the flow rate. Okay? In order for us to identify the head loss, you just simply use the Bernoulli equation. Okay, so your pressure 1 is equivalent to your pressure 2. So, change in height of 3 meters here. So, 120 kilopascal over the rho multiplied by the specific gravity, rho g, right? So, 800 multiplied by 9.81. So, essentially, we will have 18.291 and 19.113. So, solving for the head loss. So, 19.113 minus 18.291 is equivalent to 0.822. So, this is crucial, class. Again, you need to identify the head loss. So, given ka na ng head loss, you have the head loss. We are to identify now the roughness at the same, and finally, your velocity. Okay? So, using your equation here, so the equation a while ago was jumbled and we will use this equation. So, very straightforward. So, the Reynolds number multiplied by the friction factor will give us a value of 16,950 or 16,950 with the relative roughness of 0.15 millimeters. So, that will be 0.15 divided by the diameter of the pipe, which is 8 centimeters or 0.08 meters, will give us 0.001875. Okay? So, where did we get class the KS? 0.15. So, here. Galvanized iron. Okay, 0.15. Galvanized iron. So, here. Next. Where is it? Okay, where is it? So, from the friction factor of 0.025 and the relative roughness of approximately 0.02 and the what did you call this? The Reynolds number of 16,950. So, in between here. Right? So, that is 1.6 times 10 to the 4. Okay? So, here will give you a friction factor of, so intersecting or in this line. So, the intersection is friction factor 0.025. Okay? So, substituting this, we will get, by the way, class, you need to identify also the length. So, the equivalent length is simply the hypotenuse of the right triangle, 30 meters, and the height of 3 meters. So, 30.15. So, from the given 3 terms, or we have solved 0.822 from the Bernoulli equation, we identify the head loss. 0.025, the friction factor, we have identified from the Moody diagram, and the length by just simply doing the Pythagorean theorem. You can easily substitute everything and solve for V. So, right? So, V is simply the square root of 2 times 9.81. O, take note class, this is also the Darcy-Weisbach equation. Times 0.08 times 0.822. So this is your head loss. This is your diameter. This is your acceleration due to gravity. This is your constant 2 divided by your friction factor 0.025 here, multiplied by the total length, the absolute length, okay, will give you a velocity of 1.308. But we are not yet done. Okay, we are to identify the discharge. So the discharge is simply area multiplied by velocity. So that will be area pi over 4 multiplied by the diameter squared multiplied by the velocity. That is 6.57 times 10 to the negative 3 cubic meters per second. Okay. So for our next problems or next examples, stay tuned for our next lecture. Thank you all and God bless you all.